Hey everyone. So we spent a lot of time talking about elements, and it's about time that we actually get to the periodic table where they're all organized. So we're going to take a quick history lesson here, and we're going to start off with the first attempt at a periodic table created by J.W. Dobriner. So in his periodic table, he actually grouped elements in groups of three, which are called triads, and these triads were actually determined by the properties of an element. So if three elements shared similar properties, then they are grouped together. For example, chlorine, bromine, and iodine. These three have very similar properties to each other, so they were grouped together, one of those properties being their high reactivity with metals. What was actually noticed here is that one element of the trio actually had an average property of the other two. For example, when talking about chlorine with a mass of 35.45 AMU and iodine with a mass of 126.9 AMU. Their average together actually gave you a mass of about, sorry, just correct my spelling here. So their average together actually gave you a mass of 81.17 AMU, which was found to be very, very close to that of bromine. So within the triad, one element would have an average property that was the average between two other ones. The issue with this method is that not every element was actually able to be grouped up into these triads, so they had to find another way to go about organizing the elements. This is where Dmitry Mendeleev came in. Dmitry Mendeleev actually proposed the first periodic table that was genuinely accepted in the scientific community, and his periodic table arranged the elements by increasing atomic mass. So as the atomic mass of the elements increased, he would classify them together within that order. In doing so, there are actually gaps in this periodic table, which he attributed to some elements not being discovered yet. The problem with this, though, is that as he kept filling in the table with more and more elements, the way that they're being organized didn't really fit in because he was still trying to match up properties, assuming that the properties would follow the same trend as the masses, but they didn't. One example is between element tellurium, Te, and iodine. So iodine had a mass of roughly 127 AMU, while tellurium had a mass of around 128. But tellurium fit better with other elements that came before iodine, while iodine fit better with other elements that came ahead of tellurium, so he had to start making some exceptions to it. So his rule of organizing by the atomic masses didn't always work out. It wasn't until 1913 did the physicist Henry Moseley determine atomic numbers, which we know now as being the number of protons in an atom, and that's how our current periodic table is arranged by. So, following that trend, where Mendeleev had organized tellurium before iodine, tellurium's got 52 protons, while iodine's got 53 protons. So that actually fit better with matching in the properties than just following the order of the atomic mass increasing. This led to the development of what's called periodic law. Now, periodic law, in essence, just states that as you go across a row, the properties begin to change, but every row shows that same exact change. When you're going from left to right of the periodic table, the properties will basically change in the same exact way. So our current periodic table goes based on the atomic numbers increasing rather than the atomic mass. So here's what Mendeleev's periodic table looked like. It's one of the first ones ever constructed, just showing all the different elements that they knew of at the time. So you can see that these things are organized by atomic masses. As we go down these columns, the atomic masses are increasing. You'll notice that some of these actually have a question mark to them. This is because there were gaps within the masses, and these numbers here were actually assumed to follow the trend. So it actually led to the proposal that there are elements that still had not been discovered yet. And then later, as time has passed, the table started getting filled in. These question marks were actually replaced with known elements. So Mendeleev's periodic table actually helped to predict things that weren't there just yet. You can see here the tellurium and the iodine example, where the 120 had a question mark there because of the fact that he wasn't really sure if the tellurium belonged here because the mass did not fit the trend. So there were definitely some gaps there. And then again, it wasn't until the discovery of the atomic number, or the number of protons, did this get reconsidered. So our current periodic table is essentially arranged into three categories. We have our metals, metalloids, and nonmetals. Each one of these categories have got their own distinct properties. And as we go across the row, these properties actually go from being metallic to more and more non-metallic. So here's what our modern periodic table looks like. It's something that we're all familiar with at this point. So you can see that there's basically three different categories. You have this pink section, which are all metals. You have this green, the metalloids, and you have nonmetals. Now, these rows, as we go across, are called periods. So the row on the periodic table is called a period, while these groups are either called families or groups. Okay, that's what we assign the column. So a column is a group or family, while a period is the row. And again, we're going to have three basic categories of our elements. And that's how we're categorizing them by. So if we're starting off with metals, about 80% of the elements are metals. If we take a look at the periodic table, you can see that the bulk of the elements that we've discovered are what we consider to be metals. Now, the properties of metals are that they are very, very good conductors of heat and electricity, meaning that they can basically conduct an electrical current, they can transfer heat pretty well. They're usually pretty shiny. We all think of metals, we know that they're shiny, and they are normally solid at room temperature, the exception being mercury, Hg, that's actually a liquid at room temperature. They have high ductility and malleability, meaning that they can be molded. They're not very brittle. You're not going to really be able to just smash and break one. Rather, you can actually form and deform them. So next up are metalloids. Metalloids are those that are present on the staircase of the periodic table. So if we take a look here, these green ones are our metalloids. You can see kind of like a staircase between these elements. That's where there are. So only about 6 elements are considered to be metalloids. Metalloids are the midpoint between metals and nonmetals. It really depends on the conditions. For example, silicon can be a pretty poor conductor until it's actually mixed together with boron, and then it becomes a pretty good conductor. A lot of our electricity and our electronic products actually use this type of silicon boron mixture to help improve the conductivity of some of the electronics that we have. So their properties are going to be somewhat in between. Metalloids are going to be solid. They can either be shiny or dull. Again, it's going to depend on the conditions and like whatever it is you're mixing them with. And while they are better conductors of heat and electricity than nonmetals, they're not really as great as metals. So again, they're kind of like in that in-between area. Lastly, nonmetals are found in the upper left-hand corner of the periodic table. Most nonmetals are going to be found as gases. Some of them are colorless, other ones are not. Um, Only a few are going to be solid, and one, bromine, is going to be liquid. Now, the properties of nonmetals will actually vary a lot between them. So we just kind of consider the properties of nonmetals to be that opposite of metals. So you can't really give one defined property that every nonmetal is going to have, but rather you'll consider a nonmetal to have the opposite property of what a metal would be, because it's not a metal. So one example being that nonmetals are very, very poor conductors. They're not going to really conduct electricity all that well, and they are pretty brittle, meaning that you can smash and you can break them pretty easily, unlike a metal. They're not going to be easily moldable. Okay, so now that we have our metals, nonmetals, and metalloids, we can actually further classify them based on similar properties. So those groups, which again we're going to call the columns on the periodic table, actually have their own distinct name to them. So these names you consider like their family names. They kind of help identify that elements in the same column actually share similar properties. So group 1A of the periodic table we call the alkali metals. Group 2 is called the alkaline earth metals. The middle rectangle, groups 3 through 12, are called the transition metals. Group 17 are the halogens, and group 18 are noble gases. We have two rows on the periodic table that are actually removed from it, which we call the inner transition metals. So if we take a look here, we have our labeled periodic table. We see at the first column here, okay, these are going to be a different color. These are your alkaline metals. Here are your alkaline earth metals. Again, middle rectangle transition metals. When we get over here to this nonmetal section, you can classify some of these nonmetals based on halogens, group 17, okay, and noble gases. And again, noble gases are called noble gases because they contain 8 valence electrons, with the exception of helium, which only has 2, but they have that full outer shell, which is why they're the noble gases. They're the perfect elements. The halogens are the closest ones to becoming like them. And then right here, these two rows are called the inner transition metals. These were removed mainly to condense the periodic table, and because these two rows share properties that are different than the other elements here. So while we could include these two rows in this block right here, which is why they're called the inner transition metals, because they should be in there, they're actually removed mainly for the sake of how the periodic table looks and because their properties are a little different. So the natural state of an element is essentially how the element's going to be found naturally. Now, most elements found in nature are actually very, very reactive. So you're not going to really find most elements outside of a compound in just their basic one element form. Some exceptions here are what are called noble metals, so gold, platinum, and silver, along with noble gases, mainly because these elements have a tougher time reacting. They really don't have much of a need to react, so that's why they're going to be easier to find on their own compared to other elements. And many elements can actually exist as just one individual atom, which we call being monatomic. Some elements, which we call diatomic elements, are a little different than that. Diatomic elements are those elements that have to exist as a pair. They're essentially a molecule. That's how they exist naturally. They have to have two atoms bonded together. These diatomic elements are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. So these 7 elements in nature, if they're by themselves, exist as a pair, not a single atom. As a single atom, they're what's called a radical. These radicals are actually very, very, very reactive. So because they're very reactive, they're almost never going to be found on their own. When they're paired up like this together, that's how you can find them in nature. So whenever we see something like a diatomic atom, such as hydrogen, we'll see them as a pair, as H2, oxygen, O2, nitrogen, N2. Whereas monatomic atoms, which we'll see like sodium, one atom, iron, one atom, carbon, one atom. So we'll see them kind of in their one individual form. Now, an easy way to help remember this is a little acronym called Brinkelhoff. Brinkelhoff helps you kind of organize all these 7 elements, and it's just a great mnemonic device to kind of just help you remember what the 7 diatomic elements are. So again, it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. These 7 are the 7 that have to exist as a pairing. So now why don't you practice? Go ahead and classify these elements based on being a metal, nonmetal, or melanoid, and indicate their standard state, if whether they're going to be a solid, liquid, or gas, or if they're going to exist as a molecule.